considering the arch dam, the similar forces uh, such as existed for the gravity dam are also applicable herein as shown, but the uplift pressure is uh, insignificant in this case. And also, uh, when we are considering the failure types, we should consider the behavior under the reservoir filling of this arch dam. So when the reservoir water level is rising, what is happening is uh, the compressive forces develop within the dam body, and arching action transfer the compression forces to the abutments, and then cantilever section passing the compression forces to the foundation. So thereby sliding occurs at the foundation and yielding occurs at the two abutments. So, in addition to the modes identified for the gravity dam, here it suggests abutment failures also considering the concrete arch dams. So, in this case, the similar set of instrumentation that used for the gravity dams could be employed for the arch dams also. However, uh, uh, due to the solid foundation conditions that we are usually associated with the concrete arch dams, we could ignore the earth pressure cells. That's an optional instrumentation. Other than that, usually the concrete arch dams are higher than the concrete gravity dam, and therefore uh, it could accommodate several galleries along the height, and it could increase the number of measuring stations employing within the dam body. So, as an example, let's take the pendulum and the geodetic survey measurements. So they could be interconnected to check the deformations along the cantilever sections and also in the arch directions of the dam. And then we are going to see the examples of concrete face rockfill dam. However, before moving to the failure modes and loading acting on these CFRD, it is better to see the main components of these CFRDs. So the main rockfill zone is this zone, and then the cushion lay is there to support the face slab, and this is the face slab. There you can find the starter slabs, this small triangular shaped part which initially casted, and then there are several types of joints such as slab joints and peripheral joints and construction joints. Then you can find the plinth, which assures the connection with the foundation and the face slab. So when you are moving into the failure mechanisms and instrumentation, we can identify that CFRDs are subjected to internal erosion and piping through foundation, and also through the embankment and embankment to the foundation. You can imagine a case like Kotmale. There is a limestone layer beneath the dam, and there is a probability of internal erosion, and then slope instability of the both upstream and downstream phases. And next one is the overtopping. Overtopping can wash off the downstream materials and cause the phase slab in unstable condition without providing necessary support for it. And then foundation failures and concentrated leakages and any other additional damages due to the seismic activities. However, the main thing you should note here is for the concrete face rockfill dams, the face slab is acting as the impermeable membrane that hold the waters uh, without permeating to the dam's body, and therefore also you could understand that this rock-filled material is highly permeable and show the free draining condition with various filter zones and so on, and there is no pressure development within the embankment. So now we are going to consider the Kotmale, our dam, and then here you can see the section of the Kotmale and the plan view of the Kotmale. So here there are instruments to measure the foundation pressures, that are foundation piezometers, as you can see here. They have installed or along the larger section of the dam and at other two locations also, and then limestone piezometers that I have set to measure the pressures on the limestone layer, and then the settlement cells. They are hydraulic overflow settlement cells that measures the settlements of the uh, cushion layer which support the face slab, and thereby you can identify any unusual deformations occurred in the face slab due to lack of supporting, and then the embankment settlement cells that gives you an indication of the slope instability that occur due to the internal relative movements of adjacent rockfill layers that are placing during the construction stages, and then horizontal movement gauges which measures the horizontal movements within the stratified layers, and then joint meters along the plinth and subjoints, and inclinometers to measure the inclinations of these face slabs, and then the V notch to measure the wears. Also, there are survey stations to measure the surface deformations of this embankment. So now we are uh, going to see the another example, that is uh, from the Randanigala Dam. As you can see here, this is the largest section of the Randanigala Dam, and instrumentation as shown here. Uh, as I have mentioned earlier, the all possible failure modes uh, stated for the concrete face rockfill dam are applicable for this Clayco rockfill dam also. However, in addition, the liquefaction failure mode also could be considered. So here the main water barrier is the clay core, and there are field zones at the both sides of this uh, uh, core, and you can see here the upstream side of the clay core is not well instrumented because the phreatic surface is touches the core, and then you have the dropping phreatic surface and passing through the filter layers, and these the downstream rock filters should be properly monitored, and that's why this side of these uh, dam is instrumented rather than instrumenting the upstream side. So here you can identify extensometers to identify the internal deformation within the clay core, and the horizontal displacement gauges as we discussed for the Kotmale, and then the core pressure cells to measure the pressure in the clay core, and the bottom water pressure of the foundation rock mass as the downstream foundation, and then the vertical displacement gauges to measure the settlements, and then there are strong motion accelerometers also to measure the seismicity. So now we are going to see how this instrumentation selected for measuring which type of measurement. As you can see here, there are few type of embedment strain gauges. We are looking one example with the strain gauges, and you can see here the dynamic embedment strain meters. with electric resistance, and then concrete embankment strain gauges of working under the vibrating wire principles, and then high temperature embedment vibrating wire strain gauges. uh, and you can see here that the dynamic embedment strain gauges are used for dynamic measure the dynamic loading, and the electrical resistance type is selected because their response time is very low, and the other two, the concrete embedment and high temperature embedment, are a little bit slow, having little bit higher responsive time compared to the dynamic embedment type gauges. And then you can see here the dynamic type response embedment strain gauges are good for measuring the dynamic activities, dynamic measurements, what is changing quickly. And then concrete embedment and high temperature embedment vibrating wire strain gauges are better for monitoring static changes as their response time is little bit higher. Such like you can compare the what is supply provided for us, and we must select the best option what we have afford. And also here it should consider the application. So here you can see something like this arc weldable one and spot weldable one. They are also using with the steel gauges, and soil extensometer vibrating strain gauges are used for soil structures like for dams and so on. And these rebar strain meters, and here we have fiber optic strain meters usually done for force tensioning and so on. And accordingly you could see the applicability of these strain gauges is massive, but you should think on an engineering basis, and also the economy and availability also considered and selected the best possible option you can go for. So here, such as we should consider the application, its working principle, operating parameters such as range, resolution, accuracy, nonlinearity, temperature range, dimensions, and so on. In addition, price also price and availability also checked. So what we are doing using these all type of things is ultimately moving uh, heading into one particular uh, aspect, that is dam safety, and reducing the risk associating with it. So there are several guidelines to develop in this regard, and what we are doing as dam engineers is uh, we are uh, we are already trying to reduce the risk level as low as reasonably practical. In our terminology, we will say that alarm. That means ALARP. That is our utmost goal, and we could explain like this one. If we are doing a upgrading project, the blue dot shows it is prior to mitigation, and then the rose color one shows the current assessment after the upgrading. Always we need to reduce the loss of life associated with this threat and the annual probability of the dam failure. Here I have showed you one such example extracted from the ICOLD guideline on risk assessment, and uh, uh, other guidelines such as ICOL, FEMA, and USSD are also there to work in similar type of activities. So all the remedial works that we are carrying on our dams are done basically founding on this concept. So at this high time, I would like to thank our Director Engineer Sir K.R. Uppala and our Deputy Director Dam Safety Engineer Mrs. H.K. Wilbert and Ms. Amunugama for carrying out this work. And thank you all. And hope some of you may join with us in future to contribute in this endeavor to ensure the safety assurance of these important structures by joining with us. And with that hope, wish you all the very best in your future endeavors. And I will hand over this session to the next presenter. Thank you.
Okay, thank you very much, Engineer Ms. Madhubhashini Herath. So you have surfaced many important contemporary applications related to the dam safety and dam instrumentation. And importantly, you have just triggered the desire of becoming dam engineers, at least some of our undergraduates, those who are about to pass and start their careers in the upcoming weeks. And with that, we will be moving to our next presenter. He's also a product of Faculty of Engineering, University of Peradeniya, Engineer Udit Ekanayaka. So at present, Engineer Udit is working as a Civil Engineers Division of Major Dams and Reservoir Operations, Mahawali Authority. As Engineer Madhubhashini, Udit also graduated in 2014 from the same department. And Engineer Udit will talk about operation and monitoring of the Victoria Dam. Over to you, Engineer Ekanayaka. You can start.
Can you hear me, sir?
Yes, yes, yes.
Good morning, all of you. And with the time, I will manage my presentation. I think we need to. Okay.
Udit, you can take your time. Yes, we have time.
Okay.
Okay.
Sharing. Hello.
Yes, Udit, we can see your screen and we can hear you also.
Okay. In my presentation, I will briefly introduce you and the operation and monitoring of the Victoria Dam. Specifically, the Victoria Dam. Why we select the Victoria Dam? Because the Victoria Dam is the tallest dam in Sri Lanka with unique double arch curvature design, and also it's installed with almost every instrument actually for the arch dams in Sri Lanka. And also it's using modern dam engineering technologies and monitoring systems. That's why we select Victoria Dam to do my presentation today. So with that brief introduction, I will go through the specific details of the Victoria Dam. It's double arch curvature dam. Total capacity is about 722 million cubic meters and the crest length about 520 meters. Maximum height is about 122 meters and surface area at the full supply level is 23 square kilometers. Then I will show you what is the difference between single curvature arch dam and double arch curvature dam. I mentioned you that Victoria is double curvature arch dam. The dam is curved in a plane and its elevation. You can see here the difference between single curvature arch dam and double curvature arch dam. And I will introduce you some hydrological and reservoir data here. Catchment area, direct catchment 549 square kilometers, and design flood discharge. Actually, dam is designed for 1,000-year return period flood. You may all know 1,000-year return period, how to design for the 1,000-year return period. And also the probable maximum flood. We need to check the dam overtopping condition for probable maximum flood. And also reservoir full supply level is 438 meters mean sea level, maximum flood level at the 1,000-year flood, and minimum operation level, it means the power generation level, and gross storage up to full supply level is 722 million cubic meters. This photo was taken in early 1980s when the dam was under construction. You can see how the dam was constructed in 1980s. And this is section view of the dam. You can see the full supply level 438 meters, gate sea level 430 meters, and how the sailing basin was located, and the spillway and the galleries. Inside the dam there are 7 galleries for instrumentation and monitoring purpose. I will show you in later. And this is the section view of the dam. Radial gate operation. Dam is consist of 8 radial gates. Actually, we don't need any sort of power to open the gates when the water level at full supply level. With that arrangement, we can open the gates without power because of this weight of that counterweight arrangement. Then I will show you briefly how the gates operation sequence actually. When we consider the center line of the dam, we can take right bank and left bank. Right bank, we have 4 gates. Left bank, we have 4 gates. When the water level comes to 438.04 meters mean sea level, first and 2 gates are in step 1. Open for step 1 in 0.7 meters. Discharging water 156 cubic meters per second. Then step 2, when water level rises another 4 centimeters, 438.08, next 4 and 3 gates are open. Again, another 4 centimeter rise, gate number 6 and 5 open position. Then another 4 centimeters, 8 and 7, all gates open in first step. Then another 4 centimeter rise, again it starts to second stage. Like that, gates are open. This is the gate operation sequence. You can see here how the gate 1, 1 and 2 open in position. So this picture shows how it looks like in SCADA. When gate 1 and 2 open, how it looks in SCADA system really. So in previous batches were lucky enough to be there and visit themselves the Victoria Dam and operation. So, but this time with that situation, you are unable to be there. But I will show you a small video clip. Let's try to play here.
The Victoria Dam was constructed in 1985 and is the most important among the other dams due to a number of reasons. The Victoria Dam is the highest dam in Sri Lanka.
Excuse me.
Of 120.
We don't see the video playing.
We can't see the video.
Yes.
Okay, I will show it after my presentation, sir.
Okay, thank you.
This is the view from Victoria Dam control room. Actually, how it looks like our displays in Victoria Dam control room. So you can see here 8 radial gates. They are gate. Can you see the mouse pointer actually?
Yes, we can see. Yes.
Here gate position. Now it's all line 0 position. Here the capacity, current water level capacity, MCM, and here the surface area. You can see here two tunnels. These are two bottom outlet tunnels. Outlets. We have two bottom outlets to uh, discharge water in emergency condition as well, and also for mud flushing condition requirement. Um each tunnel consists of two gates. Here you can see two pumps actually to pump out the seepage water from the dam, from which are collected inside the bottom gallery G of the dam. This is in case of repair purpose. From here we can put stop blocks to repair these gates. So this is where we put stop blocks from using a crane. We can lower the stop blocks to block these bottom outlet sluice and repair the gate. And for gate repair works, we can use gantry crane located on top of the dam to lower the stop blocks to block the water flow, and we can do the maintenance of the gate. Next, I will go to my main part of this presentation, dam instrumentation and monitoring. Actually, previous presentations, you all get to know the purpose of monitoring dam available instruments like that. But I will illustrate you specifically what are in the Victoria Dam. So why dam monitoring? Actually, you all know now. We need to identify defects of the dam, cracks, joints, tilt, inclination, stress strain, deformation, seepage flow, etc. And also we need to develop some behaviors of the dam. Why dam monitoring? Physical data are very important for assessing the safety and performance of dams. Like that, these are the physical data available: movements, water pressure, seepage, reservoir water elevations, local seismic activities, stress and strain, internal concrete temperatures, like that. Then these physical data are measured and monitored by the instruments and equipment. This one I was taken from Angola. You can see the cracks appeared in that dam because of alkali aggregate reaction, specifically the alkali silica reactions caused by these type of crackings, and some kind of concrete deteriorations may occur. So we need to monitor the dams very carefully. Monitoring dams saves life, as really area can be evacuated before landslides, move dams, break, tunnels collapse. So, and also it saves money and much more things. How we monitor the Victoria Dam? Actually, we have specific guidelines for the monitoring purpose. As you can see in this figure, we have operation and maintenance manuals, and we refer some safety and evaluation books available, and inspection reports we are preparing, and also data analysis. From projects, we are time to time upgrading our instrumentation and monitoring systems. I will show you later on in my presentation how we have done our upgrades. Okay, let's move with my presentation. And this is the instruments available. Some sort of instruments: normal pendulums, inverted pendulums, extensometer, piezometers, drainage flows. Drainage flows we are measuring using actually seepage. Then kilometers, strong motion accelerometers, and a peer distance measuring device, vertical deformation measuring device, vibrating wire instruments, and also real-time dam monitoring system. I will show you each and every instrument and method in later in my presentation. Uh, Here, why these instruments are using for dam deflections, foundation deflections, and what sort of frequency we are taking in instrument readings. Normal pendulums, 2 weeks time, like that. Here I show you. You can see the duration of the instrumentation reading we have been taking, and also the purpose of each and every instrument. I will discuss it it with you in later. And here also concrete frames, we are using vibrating wire strain meters, vibrating wire thermometers. For foundation hydrology, we are using piezometers, spillway pier, pier distance measuring device like that. For instrumentation data analysis, we need to definition of axis. For in our terms, we are using axis definition because when we analyze the instrument data, we need to have some sort of graphical and also some sort of conclusion how the dam has moved for upstream, downstream, to left bank, to right bank, like that. So our definition is, you can see here, positive towards right bank, it's taking right bank to left bank, so we are taking right bank as positive. And y downstream upstream direction, we are taking downstream positive, then z upward and downward, so positive upward, like that. Then I will show you next few slides in what are the instruments I mentioned earlier and where they located. Here, normal pendulums. We have inside the dam, we have several, I mentioned you, we have 7 galleries. So in 7 locations, we have normal pendulum shafts. In red color, you can see these shafts. Each shaft, we have normal pendulum. So when we go through these inside the dam, we can go through the dams, we can take readings in different locations. This is how it arranged in gallery G, bottom gallery. The G means bottom gallery. In it's located as a oil bath, and from this table we can take the measurements from that table. Then we analyze this into the directions, as I mentioned earlier, XY direction. We can use a T-square as mentioned, as shown here, and also a upgraded scope. From there, we can take instrument reading for up to 0.01 millimeter accuracy. This is the scope we are using to measure the pendulum reading. And inverted pendulum. Actually, inverted pendulums. What is inverted pendulum? It's like um, drilled hole towards to the dam foundation, and the pendulum cable has anchored to bottom, like 30 meters, 40 meters depth. Then here in gallery G, bottom gallery, we can take the readings. There's a floating bucket. From there, we can take the readings using a scope, like that. This is the floating bucket. This is the anchored hole. We can take readings using a given scope. And here you can see some sort of one analysis. We are doing a huge number of analyses over the years, and we'll be predicted, and we are predicting reversible movement, irreversible movement, such things. This is one sort of analysis. And data analysis shows the conclusion, some sort of upstream movement, and it is very common stuff for each arch dams in the world. Extensometer. Here you can see extensometer location. Extensometer is actually using for the measurement of foundation displacement with respect to the gallery G foundation flow level. You can see the extensometer located in gallery, bottom gallery. We are using this instrument dial gauge to measure the displacement of that extensometer. It's like a 3-point extensometer. 3 holes there located in 60 meter, 35 meter, and 15 meter depth. From that dial gauge, we are measuring the displacement of that bottom anchored point with respect to the gallery G flow level. And this sort of analysis from extensometer and drain holes and piezometer. Yes, we in arch dam, all arch dams and has a drainage curtain and also piezometers. You can see here in this figure our drainage holes. They are in this in middle. They are about 100 over 100-meter depth. So from drain holes, this is the locations of piezometers. We have 23 piezometers. You can see how they have located. They are located in the dam and dam site. This is one cleaning when we were doing the cleaning of the drainage holes, and you can see the drainage flow of the dam. This is actually to release the pore pressure built inside the foundation. And also we are using the V-notch weir arrangement to get the accurate seepage values. And you see the seepage data and how it behaves, and clinometers. Then next, what is clinometer? Clinometer is using for the measure the rotational movement of the dam. So we have 5 number of pairs of clinometers, and in inverted pendulums you can see these are old clinometers, but in 2016 new clinometers have been installed. With that we can measure very accurate movements in the gallery G, how gallery and the concrete of this bottom foundation is rotating with respect to the dam axis. We can measure using these clinometers. And strong motion accelerometers. Actually, in past recent time, very useful and very uh, yes, in every news, and you can see the SMA data and how it was recorded in the dam. You we need to measure the earthquake vibrations. So how that vibrations effect to the dam body. So we have 3 SMAs, one in actually in abutment, it is not connected to dam, it's in solid rock location, and other two in inside the gallery, as you can see here, in P2, in P gallery G. And this is the photo of that located strong motion accelerometer. From that, we can measure the earthquake vibration, as I mentioned earlier. How it is recorded, this is one recording we have obtained, and I will show you again. We can measure up to that kind of accuracy, 0.0005 G accuracy. This is very sensitive instrument. You can see how it is measured using how the data have been received. You can see here 6 earth tremors recorded since 29th of August, and highest peak acceleration was recorded in 18th, about 0.01 G, and we can compare with the design earthquake loadings. And gate pier measurement device. We need to measure the gate pier movements of gate piers. So we have installed gate pier measurement devices as mentioned, as shown in here. If there's any kind of movement in the between these gate piers, we can measure using these instruments, because it directly affects to the operation of the gates. And this is while installation of spillway gate pier measurement device. And another instrument is vertical deformation measuring device, actually VDD. This one we are using to measure the vertical deformation of the dam. If the dam moves upward, like a concrete structure moves upward, we can measure from this instrument. So with that target, this is the measuring arrangement, how we are measuring the VDD readings. And here it is located in this gallery. So anchor, it's the VDD instrument anchored here location, then cable comes here, and the measuring arrangement, measuring location is this. So if the dam body moves upward, we can measure from the bottom gallery. And VW instruments, vibrating wire instruments. We have now many number of vibrating wire instruments which were embedded inside the concrete structure when it was constructed in 1980s. You can see here the numbers, and this picture was taken in when the construction was going on in 1980s. how the vibrant instrument group. This one group consists of strain gauges, thermometers, and other sort of character gauges like that. They are in groups. They were embedded to the concrete structure while the concrete was pouring. And this shows how the instruments were allocated. And we have central instrument reading chamber located inside the dam. From there, actually, it's the central hub of the vibrating instruments. All vibrating wire instruments readings come to the this location. Then we can taking this instrument to our main control room. From there, we are taking all the instrument readings and analyzing. Next, I move to geodetic survey system of Victoria Dam for movement monitoring. This is, we are proudly saying, the first time in Sri Lanka, and it's really in the world as well. We are upgraded Victoria Dam to real-time monitoring system. I will show you. This as you can see here, we have installed a 72 number of monitoring prisons. These red dots all are monitoring prisons. Then we positioned two robotic total stations from here and there. Automated robotic total stations. This is the total station we have used. We are using Trimble S9. You can see the data of that instrument. So very accurate. Actually, we can take very accurate readings from that. As you can see here, it is installed in two solid pillars. So don't want any sort of movement there. So we install them on a solid pillars. Apart from the prisms, we have another control prisms. 7 number of control prisms located in solid positions, because from that we can check whether the total station pillar has moved or not. These all control prisms have installed on a solid base location. This is how it works. From one side, we are taking readings from respective prisms, and also from other side also we are taking. And actually, this is, we are taking coordinates, real-time coordinates of that prism. So we have initial coordinates, we have current coordinates, so we can correlate them and get the movement of 3D movement of the dam. Also, we can connect from the instrument position on instrument location as well to check and rotate the total station manually to take manual readings, and also it's fully automated. And this is how it shows in Trimble 4D web map view. You can see green color, blue color, because we have set some alarms. If some prism moves more than expected, we can obtain a alarm, or we can obtain an alarm saying that prism has moved more than expected. So that alarm system also very useful in this monitoring system. And also specific location in gate pillars, we have gate pillar prism to check whether the gate piers have moved, and you can see the data when we are receiving. And also, apart from the piezometers and apart from the prisms, we have 3 number of GNSS, geographical navigation system and satellite system. So 3 GNSS have been installed, and 1 water level piezometer has been installed. So all GNSS data also lively receiving to the dam control center. As you can see here, this is GNSS installed on top of the dam. And this is how the data flow occur. All instruments goes to Trimble 4D control system. Then we can view, analyze, and can get alarms, notes, prepare reports from that control system. Victoria Dam Control Center. This is the control room. We are getting all the instrument data, all the gate monitoring data, all have been monitored 24 hours in this main control room. Hydrometeorological data. So we have some sort of hydrological database. You can see here real-time reservoir water level, reservoir daily inflow and discharges, precipitation, evaporation, temperature, and wind speed, so on, and other sort of data also we have. I will show you how we are obtaining these data. Reservoir elevations, actually we are maintaining each and every day, and actually real-time water level data we have with that SCADA newly installed SCADA systems. And weather stations, we have several weather stations. This is one HMIS weather station, and we have separate weather web portal. So you can obtain real-time weather data from that web portal. And water level sensors, weather station on top of the dam. From that, we can get this weather data: wind speed, relative humidity, precipitation, wind direction, solar radiation, and temperature, as you can see here. And we have another portal in Dam Control Center in Kolgola, so we can predict how the rainfall will be in future, so we can take actions. And dam and reservoir periphery. Upstream inspection, actually visual inspection is sort of must. We should do visual inspections. Upstream inspections are being conducted, and downstream inspections, how we are doing, it's kind of risky, but still we have to do. And water quality data analysis, we are taking water samples from each location, analyze water data, water quality data, and we are preparing reports. And periphery inspections we are conducting, and yes, we have emergency action plan. In any case of emergency, we have emergency action plan. And downstream inundation maps, yes, in case of dam breach or overtopping, we have prepared inundation maps. In that we can get how many area have been will be inundated. So evacuation process, and people will be evacuated. So inundation maps have been prepared, and we are ready to conduct any sort of emergency. And we have visitors observation gallery in Victoria Dam. So we do some introduction purposes, and we deliver some lectures there. So we welcome you all after these situations. Visit the Victoria Dam and have a knowledge. And after this situation, so you can have a look around and yourself what we are doing, what upgrades, what instruments using. So welcome you all to visit the Victoria Dam and other dams we are maintaining. With that, I will conclude my session. Thank you. Thank you all for listening. Thank you, sir.
Okay, thank you, Engineer Kanayaka. So like the other two presentation, this is also very informative presentation. Okay, then we'll be moving to the discussion session. So I would like to invite all our experts from Mahawali Authority, Engineer Halapitiya, Engineer Ms. Herath, and Engineer Kanayaka. So students, this is your time. If you are having any questions or anything to clarify from our experts, you can raise your hand and you can ask the questions. Any questions from the students?
Excuse me, sir.
Yes. Yes, Satsara, you can ask the questions from our
Uh,
experts. Yes.
Sir, I have some question regarding the manuals that they are referring about the reservoirs maintenance. What they are basically, my question is, what kind of manuals that they are using, or there are different kind of techniques about the maintenance and monitoring systems now, sir? They are using British and USA combined design manual, so whether they are specifying some kind of one specification.
Okay,
That is the
Satsara.
question, sir.
Okay, thank you. Engineer Ganayaka, did you get that question?
So actually, even though I had mentioned few examples,
Yes, Engineer Herat, we can hear you.
though I had although there are several guidelines which have been internationally recognized and well developed so far, we also refer to them, and we have developed a tailored SOPs for our dams. In each dam, we have separate operation and maintenance manuals that are specifying what activities to be done in which way. So they are specifically developed for each dam depending on each dam's characteristics.
Okay, thank you. Any more questions from the students or any clarifications?
Excuse me, sir. Can you hear
Yes,
me?
yes, Premachandra, you can ask.
I was disconnected a little while ago. I don't know if this discussion was raised before. Anyway, I wanted to know when during dry seasons, I mean when the water level is a little bit lower, what are the issues that are related to the stability of the dams that we have to face? I mean, most of the cases are related to the high tide level occasions now. So in that cases, what are the issues related to the dam stability and the failures?
Okay. Yes. The question is about the stability of the dam during the dry periods.
Actually, can you hear me, sir?
Yes, Engineer Kanaka,
Actually,
please.
we are taking readings. Actually, we are doing surveys in high flood level, actually low flood level. When the water level is lower, we are doing separate monitoring sessions, like that's low water level, pendulum data, low water level, other dam monitoring. So we have separate data set for low water level. We have separate for high flood level. So we are conducting analysis over these dams have been constructed over, have been in operation over 30 years. So we have 30 or 35 years data set in both low water and high flood levels. So both we are analyzing how the dam is moving in low dry season level. Dry season, you mean low water level and high water level. So with that, we have conclusions, reversible movements. I mentioned in my presentation that movement, reversible movement, irreversible movement, like that. We have analyzed all the data in that two conditions. With that, Same situation. I mean, same risk with that high, even though it's high flood level, low water level, same risk, same deformations. So no different. So track monitoring, all the monitorings we are conducting both in high water level, in low water level. So I think there's no different risk. So risk is same. With that, we are analyzing and monitoring the dams in same condition with both conditions.
Okay, thank you very much. Any other questions or clarifications?
Sir, I have a small question, sir.
Yes,
And
Sandra.
I'm sorry if it was mentioned in the presentations because I was disconnected several times during the presentations. My question is, in recent times we heard about some minor earthquake events in this area. So if something like that happens in the future, how is the preparation for a larger event, and what will be the effect of that?
Okay.
Okay, during last, of course, within 1.5 years from August of 2019, the tremors are started. We have recorded 6+ tremors reading. The maximum also is very small compared to the design design G, the design acceleration. That graph, comparison graph is the tremors are very small compared to the design G. Design G. Now we have 3 accelerometers installed in Victoria Dam. We can measure all tremors and all are recorded there. And then after that, you know, not the geological, GMBS, GMBA, GSMB, yeah, they have installed another 10 accelerometers. Actually, those are seismometers. It is a German research, and combined with the German Research Center and Sri Lankan Geological Department. They are observing what is happening in the area. I think no can't do anything with the very big earth tremor. We are observing and recording tremors. That's all.
Okay. Thank you very much. And students, we have a few minutes. I can allow one more questions for the students if you're having anything to ask. Yes, Ratnayaka.
Sir, in the presentation, we have heard about the Polganda barrage, and it was diverting the water to the Ukwela power plant. And I wanted to know that the Polganda barrage is highly affected to the sedimentation issue. What are the mitigation issues that we have taken to overcome that problem?
Okay. Did you get the question?
So we didn't hear actually.
Okay, so the question is about the sediment accumulation. The student is asking about the Polgolle. So generally you can talk about the sediment accumulation and the mitigation measures the authority has taken to control this sediment accumulation and the impact due to the sediment accumulation to the major reservoirs and the dams.
අපි ඒක කරනවා අපි විශ්වාස කරනවා අපි දැනට
Actually, sir, we are conducting bathymetry surveys. You know, some sort of, you may have heard the word students, maybe. Bathymetry surveys, we are conducting these surveys time to time, actually like annually or twice a year, to get to know how the reservoir capacity now at the moment. So with that, in Randenigala, we have already conducted, and Kolgolla, Rantabe, Potmale also. So with that, we get to know that the sedimentation is not kind of threat up to now with that result. But in Polgolla, you know, time to time, full Polgolla and Rantabe. Also, we are doing some sort of kind of sediment removal program time to time. So with that, we are hoping that sedimentation will not be an issue, threat to the design floods and also design capacities up to now.
And especially Polgol and the Rantambe are not reservoirs. They are not storing water, just diverting and power production while flowing. Then sedimentation is not a big problem in Polgol and Rantambe.
Right. So thank you very much. Actually, we are consumed the time more than we have anticipated. So I would like to thank the resource person again for sharing the ideas and eradicating the doubts based on the questions raised by the students. So to wind up this webinar, for the concluding remarks, I would like to invite Dr. Chamindu Deepagoda. He's the overall coordinator of this civil engineering field camp for this year. Dr. Chamindu, you can.
Mr. Daham, can you hear me?
Yeah, sure. Yes, we can hear you.
Good morning to all of you, and thank you very much for this opportunity to deliver a vote of thanks as the overall coordinator of this civil engineering field work. And as you all are aware that unfortunately the current pandemic situation did not permit us to conduct any of our field visits physically, so we were compelled to do everything online. So we completed three visits before, and last night we successfully completed our field camp within all the constraints and to whatever the capacity we put. And in today's field visit, the irrigation visit marks the end of all our field visits. And I believe this is a wonderful way of conducting an online field visit by means of a webinar, which could benefit a large number of participants. And in this regard, I would like to thank all the resource persons for your valuable contribution and sharing your knowledge and experience with the students in a situation that we could not make any physical presence in your sites. And also we are very grateful to Engineer S.R.K. Arupala, Director Major Dam and Reservoir Operation, Mahaballi Authority of Sri Lanka, for facilitating this event, and also Engineer Janak Asanta for helping in organizing this event, and also Engineer CBA Kanaka for helping organizing this event, and also playing as a resource person. And we are also thankful for all the participants attending this webinar. And Mr. Daham deserves a very special thank for organizing this from the department. And amid a lot of other academic commitments actually. So we have a lot of academic work going on during this period in the department, including examinations. Thank you very much, Mr. Baham, for taking all the trouble for organizing this event. And students, thank you very much for your participation. And I hope you had a very fruitful day today with valuable knowledge from many experienced persons in the industry. And also please proceed to the next things, including all the assessments related to this following up this event. And once again, thank you for all of us for your contribution today. And let me wind up my brief word of thanks and back to Mr. Dahan.
Okay. Thank you very much, Dr. Deepa Goda. And with that, we will come to the conclusion of this webinar. Again, I would like to thank all the resource person and also all these engineers, those who have been helping in different degrees for successfully organizing this webinar, representing the Mahawali Authority. And also we will expect the continuous support of the authority in our upcoming field visits and also these student staff and interactive activities we are planning in the future. So with that, we will wind up this session. Thank you very much for our experts and also to the students and also the members of the staff for taking part in this webinar. Thank you very much and meet you again with another fruitful event. Thank you.